Imagine a heavy industrial port of 1 million tons hanging directly on a steep vertical cliff. Beneath this structure lies no solid ground, only a 600-meter drop into deep water. Here in Norway, engineers are building a high-tech logistics hub suspended entirely in mid-air. The location is extremely hostile, subjected to constant high winds and aggressive salt mist corrosion. Every single steel plate is under constant tension, creating a severe test of material fatigue. To anchor this massive weight, the construction process must begin deep inside the solid rock. Heavy drilling rigs bore shafts 120 meters deep into the dark basalt. These shafts must be perfectly straight, avoiding any internal fractures in the mountain geology. Special high-strength steel alloy rods are slowly inserted deep into these horizontal rock tunnels. The anchor bolts are made of titanium chromium cobalt to resist long-term chemical decomposition and stress. Liquid polymer grout is pumped into the shafts under high pressure to secure the anchors. The grout expands slightly as it cures, creating an unbreakable mechanical bond with the basalt. On the outer cliff face, massive steel foundation plates are bolted directly to the rock. These plates distribute the enormous pulling force of the hanging structure across a wide area. No human workers are allowed near the cliff edge due to dangerous wind gusts. Instead, heavy robotic crawlers carry out the precise positioning of the primary support beams. The first cantilever beam projects outward over the open ocean like a giant steel finger. This beam is hollow, designed as a steel box girder to reduce dead weight. High-strength tension cables are connected from the outer tip back to the rock anchors. The tension in each cable is monitored in real time using built-in fiber optic sensors. These sensors feed data back to a central processor to prevent catastrophic structural failure. The next phase requires assembling the massive secondary crossbeams over the abyss. Industrial technicians in heavy safety gear secure structural node points inside the cold steel frames. They work in absolute silence, focusing entirely on tightening the massive high-torque bolts. No verbal communication is used. They coordinate purely through programmed hand signals. A specialized heavy gantry crane travels along the newly installed steel rails. This gantry positions the prefabricated steel decks that will form the harbor platform. Each deck segment is hoisted with millimeter precision to avoid damaging the main frame. High-powered laser tracking systems guide the crane operator from the cliff control room. To counteract the heavy ocean winds, dynamic counterweights are installed inside the hollow beams. These heavy lead blocks slide back and forth automatically to balance structural stress. The movement is controlled by a microsecond feedback loop measuring real-time wind shear. Now, the first structural support columns must be welded to the lower cliff anchorages. Industrial welders execute flawless multi-pass welds under local vacuum hoods to prevent air pockets.
The engineering here is unprecedented. This structure alone required over 50,000 tons of steel, suspended directly.
With the primary columns secured, the structural framework achieves its initial self-supporting equilibrium. Now, the assembly of the massive multi-tiered cargo deck modules must begin immediately. Heavy transport vessels deliver these modular frames directly below the hanging cantilever arms. Gigantic industrial winches on the top deck lower heavy braided steel lifting lines. Technicians on the wet sea-level platform secure the heavy carbon fiber hoisting slings. The lift begins slowly, defying gravity as 500 tons of steel rise vertically. Guiding cables prevent the heavy load from colliding with the sharp basalt rock face. As the module reaches its target height, hydraulic alignment pins extend from the frame. These solid alloy pins lock the new deck into the main cantilever superstructure. Heavy, high-torque industrial impact wrenches secure the secondary structural connection plates. Silent technicians check each bolt thread with specialized electronic depth gauges. No words are spoken. They verify their work by applying bright yellow inspection paint. The main vertical cargo elevator shaft is now integrated into the Cliffside structure. This massive hollow steel column will house the heavy high-speed industrial lift cabins. Each elevator is designed to move 50-ton containers from sea level to the top. These colossal lifts require massive magnetic induction motors to counter the immense gravity pull. We install superconducting copper coils inside the drive units at the top of the cliff. Technicians in protective suits align the magnetic track segments with micro-level precision. They apply specialized synthetic grease to the guide rollers using pressurized industrial sprayers. The elevator cables, made of ultra-high-density carbon fiber strands, are slowly threaded through pulleys. Each cable strand can support 3 times the weight of a standard steel equivalent. With the cargo lift system in place, work transitions to the primary docking platforms. These platforms must extend 60 meters out from the cliff face to reach deep water. Heavy hydraulic stabilizers are mounted at the bottom of the platform frame. These pistons absorb the dynamic impact forces of berthing container ships. Silent workers torque the heavy-duty mounting brackets using calibrated hydraulic pumps. They verify the structural alignment using precise digital optical transits on stable tripods. To prevent oxidation, a sacrificial zinc anode array is welded along the splash zone. Automated plasma cutters slice through thick steel reinforcement plates with extreme heat. Each finished weld is immediately scanned with non-destructive thermal imaging cameras. Any hidden structural defect at this stage could compromise the load-bearing capacity of the platform. With the docking deck fully secure, we begin assembling the automated high-speed cargo conveyor belt. This massive track will transport containers smoothly across the cantilever frame without human intervention. The conveyor frame is constructed from lightweight, carbon-reinforced composite materials to minimize dead weight.
This massive conveyor system is the heart of the operation, moving over 1,000 tons of raw material every hour deep into the rock face.
We install powerful electromagnetic linear motors along the conveyor tracks for continuous propulsion. Industrial technicians in heavy protective gear carefully lay down the segmented copper tracks. They work in absolute silence, aligning the electromagnet modules using high-precision digital calipers. Each motor unit is sealed inside a watertight composite casing to prevent saltwater ingress. Power cables are routed through internal conduits running inside the hollow cantilever structure. These heavy-duty cables carry high-voltage current from the main Cliffside power substation. The substation itself is carved deep inside a dry granite cave behind the cliff face. This secure cavern protects the sensitive electrical transformers from violent coastal storms. Giant high-velocity ventilation fans continuously cycle dry air to prevent internal condensation. Heavy steel blast doors seal the cavern entrance, keeping the salt spray completely out. With power routing complete, we focus on the advanced automated terminal operating software systems. High-speed fiber optic networks connect every sensor directly to a centralized neural control unit. We boot up the primary processing mainframe, located in the secure underground server room. Rows of heavy-duty computing blades hum softly under high-efficiency liquid nitrogen cooling systems. Technicians in anti-static gear monitor the initialization sequence on large overhead command screens. They verify data transmission integrity across thousands of structural stress monitoring points. Now, the ultra-heavy cargo container cranes must be erected onto the main platform rails. These specialized cranes are engineered with a lower center of gravity to counteract high winds. They are hoisted onto the tracks using the main vertical heavy lift rigging systems. The crane wheel assemblies are aligned with the high-strength rails down to the millimeter. Silent technicians torque the heavy-duty rail clips using hydraulic impact wrenches in sync. They check the final physical clearance measurements using precise electronic laser slide gauges. Powerful hydraulic buffers are installed at the extreme ends of the travel tracks. These heavy buffers prevent any runaway movement of the crane frames during severe storms. Auxiliary diesel generators are mounted on the rear structure to provide emergency backup power. These auxiliary engines guarantee that the terminal remains fully operational even during total grid blackouts. We now initiate the dynamic stress testing phase of the entire suspended structural assembly. Heavy ballast containers are loaded onto the platform to simulate maximum cargo operating capacity. Giant hydraulic vibration rams are attached to the main cantilever joints under the deck. These powerful rams begin to vibrate, simulating the violent harmonic frequencies of extreme storms. Sensor arrays continuously measure the physical displacement of the steel D/M over the abyss. Every single movement must fall within the strictly calculated safety threshold of 5 millimeters. The data is processed instantly, validating the resilience of our heavy-duty anchor design. With the physical test successful, we begin the commissioning of the automated docking laser arrays. These high-intensity sensors will guide massive ocean liners into the suspended berth safely. They project invisible scanning matrices across the shipping lane to map vessel approach speed. Technicians in the main control tower run final calibration diagnostics on the optical transceivers. The system response time is verified to be under 10 milliseconds for safety. The first commercial container ship is now cleared for its historic approach sequence.
This massive container ship, the Global Causeway, is one of the largest to dock in Britain. It's capable of moving over 20,000 TEUs in a single journey.
The massive container ship aligns perfectly with the suspended docking platform as thrusters churn. Automated mooring arms swing out from the cliff base, locking the ship's hull into place. Heavy electromagnetic locks engage with a powerful hum, securing the vessel against tidal swells. Colossal yellow gantry cranes glide smoothly along the rails to begin the unloading sequence. The crane spreaders lock onto the first 50-ton steel container with mechanical precision. Containers are lifted high into the air, transferring from ship deck directly to conveyor tracks. The automated high-speed conveyor belt activates instantly, moving cargo towards the vertical elevator. The heavy elevators slide rapidly up the vertical shafts, carrying tons of freight in seconds. At the top terminal, cargo is seamlessly loaded onto heavy transport trucks for inland distribution. This massive hanging machine proves that engineering can rewrite the rules of global commerce.